In solving a truss problem, the first step is to find the reactions at the supports. In this case, we have a very simplified tower with a cable coming off the very top, causing a force P at point D. The reactions will be at points A and G. In order to get to this point, we need to first take the force P and separate it into its components. So here's P, and it has horizontal and vertical components. Call them Px and Py. If we take all angles with respect to the positive x-axis, this angle of 15 degrees actually becomes negative 15 degrees. And our x component will be P times the cosine of the angle. Py will be the magnitude of P times the sine of the angle. We'll assume that P is 10 kilonewtons. And our calculations then will look like this. 10 kilonewtons times the cosine of negative 15 degrees, which results in 9.66 kilonewtons. The vertical component, Py, will be likewise 10 kilonewtons times the sine of negative 15 degrees, which is negative 2.59 kilonewtons. Now that we've broken our angled force into components, and if we had other forces, we'd have to make sure that they were also into the horizontal and vertical components. We next move to summing the moments about points A and G. As we add up the moments about a point, in this case we're adding up the moments about point A, we use a force, in this case say Px, and we multiply it by its perpendicular distance. So if Px is going here, we need its perpendicular distance to point A. Here's its line of action. We are looking for this distance here. Its perpendicular distance to point A. We'll call this lowercase d y. So this would be Px times dy. And when we add up the other forces, moments, we take those forces, such as Py, and we will multiply them by their perpendicular distances, in this case dx. we find dx, identifying py on the diagram, and finding its horizontal distance because it is a vertical force. And here is 7 meters, 3 plus 4. This is the line of action of py. It is a perpendicular 7-meter distance from point A. Now there are other forces involved. At point A, we have a pin. This pin can take forces in both the y and the x direction. So we have AY and AX. If we remove this pin at point G, we have to replace it with GY and GX. So we now have 1, 2, 3, 4, 5, 6 forces in this system. So AY, AX, GY, GX. Next, we need to fill in all the distances for each of these. Seems overwhelming, but it's fairly easy. The distance from point A to point A is 0. There's no distance. It's the same point. So this gets multiplied by 0, and this gets multiplied by 0. So we can ignore those. GY is a vertical force, so we need to find its horizontal distance from here to here. From G to A is, just add these up, 3 plus 4 plus 4 plus 3 meters makes it 14 meters. One might be tempted to say that GX is the same, because the distance from point G to A is 14 meters, but it's not the distance from point to point, as it is the perpendicular distance of the force. GX's line of action goes straight through point A. So the distance from GX to A goes right through, is 0. So this simplifies things greatly. The sum of all these moments must equal 0 for a system in static equilibrium. Let's write this again and simplify things and plug these numbers in. Px is 9.66 kilonewtons. And its distance, y, is 15 meters, 3 plus 6 plus 6. P in the y direction is negative 2.59 kilonewtons. And its perpendicular distance was 7 meters. We have 0 here, 0 here. Finally, GY times 14 meters. Now, GY is an unknown. So it's the only unknown in the equation, so we can solve for it. All of these add up to 0. One thing remains. We still need to find the directions of these moments. By convention, clockwise is negative and counterclockwise is positive. This 9.66 kilonewton force, Px, is going in this direction around point A. So that's clockwise. That makes it negative. The 2.59 kilonewton force, Py, is also going in a negative clockwise direction around joint A. So it is also negative. Gy we don't know. I have it drawn as a positive, and I will assume that it is positive until proven otherwise. So if I assume the force is positive, not the moment, assuming the force is positive, because we're trying to find the force, about point A, it's got a counterclockwise rotation. So we will assume that this moment is a positive moment about point A. Writing all of these, multiplying them out, we end up with negative 144.89 kilonewton meters minus 18.12 kilonewton meters plus Gy times 14 meters equals 0. Combining these two terms, you have negative 163.01 kilonewton meters plus Gy times 14 meters equals 0. Now we'll add 163.01 kilonewton meters to both sides. And we have 0 Gy times 14 meters equals 163.01 kilonewton meters. And if I divide both sides by 14 meters, I end up with my value for Gy. Gy is 11.64 kilonewtons. Next, we will sum the moments about point G to find the reaction AY. We'll do it in the same manner as we did around point A. So I sum the moments, point G, they must equal 0. And I will list off my 6 forces. Px, Py, Ay, Px, Gy, and Gx. Now I will find each of the distances. So for Px, we'll need this dy. For Py, we will need a dx. So we'll need a horizontal distance for vertical force and a vertical distance for horizontal force. Ay is a vertical force and is 14 meters from point G. So it's a horizontal distance from A to G. Ax, in the same manner as looking at Gx in the previous, goes straight through point G, so its distance is 0. The distance from G to point G is 0, and the same goes here, so that helps us immensely. So our equation looks like this. 0 equals Px, which is 9.66 kilonewtons, plus 9.66 kilonewtons times the distance. The vertical distance is, again, 15 meters, plus Py, which is negative 2.59 kilonewtons, times this distance here is again 7 meters, 3 plus 4. Add that to AY times 14 meters. And again, we need to look at the directions for each of these moments. For the 9.66 kilonewton force, that's Px, going around point G. Let's go in this direction. So it's clockwise. That makes it negative. The 2.59 kilonewton force, although it is a negative force, it actually is causing a counterclockwise motion around point G. So that makes it positive. AY, we don't know its direction, drew it in as positive, so we assume the force is positive, which makes it go in this direction about point G, a clockwise motion, a negative moment. All right, evaluating each of these. Zero equals negative 144 kilonewton meters plus 18.12 kilonewton meters minus AY times 14 meters. Combining these two, 0 equals negative 126.77 kilonewton meters minus AY times 14 meters. And we will add AY times 14 meters to both sides. And these will cancel out. So on this side of the equation we have AY times 14 meters equals negative 126.77 kilonewton meters. Divide both sides by 14 meters. And that cancels out with that. That meter cancels out with that meter. And AY is negative 9.05 kilonewtons. So although I assumed AY was going positive, it ends up actually. So the next thing I need to do is check to make sure that I've done my calculations correctly, and I can use the addition of all the forces in the y direction, and required by static equilibrium, they must equal 0. So all my forces in the y direction, I've got py, ay, and gy. So in alphabetical order, ay plus gy plus py. AY is negative 9.05 kilonewtons. GY calculated as 11.64 kilonewtons. And PY is negative 2.59 kilonewtons. If I add up 9.05 with a 2.59, that adds up to negative 11.64 kilonewtons. If I add 11.64 kilonewtons, I find that 0 equals 0, and my values check out. If I go on to add up the forces in the x direction, and they must equal 0, I have AX plus GX plus PX. Problem here is I have one equation and two unknowns. I have AX and GX as unknowns. I have PX up here, but I need another equation to determine AX or GX. If G had two struts coming off of it, this would be a statically indeterminate problem, and we would not be able to calculate this based on statics alone. But since it only has one strut, we can use the properties of struts to determine our gx based on our gy that we calculated before. Now that we've determined using summing the moments about point A to find gy and summing the moments about point G to find AY. Then we added up the forces in the y direction and they found they equaled 0, so we were checked up on that. Then we looked at the forces in the x direction and realized that we didn't know two of them with only one equation. So we need to find something else that can help us. Let's mark off this section here. This strut FG, because it's a pin-loaded structure with only 2 pins, it has only 2 locations for these forces, so we have and the forces at this pin. This is what makes it a strut, or if it's in tension, a tie, but we'll just refer to it as a strut at this point. Because of this setup, 2 pins only. If it were 3 locations, this would be a beam and bending possibly, but just because it has 2 pins, it's a strut. Therefore, the forces go in the same direction as the geometry. That means I can use the geometry to determine the forces. What does that mean? If we look at the forces and consider them, the force on FG in the y, and its ratio to the forces on the strut in the x direction, they will be equal to the distance of FG in the y divided by the distance of FG in the x, which is actually equal to the tangent of the angle of FG. We weren't given angles here, so I will ignore the tangent, but the relationship stays the same. If you had the hypotenuse, we could use the hypotenuse and the sine and so on. So these forces are related in this manner. What's more, point G, we have the reaction loads of Gx and Gy. So Gy and Gx, in this case, are the same as the forces on the strut in the y direction and the forces on the strut in the x direction respectively. So this is Gy over Gx. Well, what do I know? I know these distances, and I know G in the y direction. That gives me an equation with one unknown, Gx. So I can rewrite this solving for Gx. Gx equals Gy times the distance from F to G in the x direction divided by the distance from F to G in the y direction. Now, very carefully note that there is a negative in here. Actually, so this will affect our result. So Gy is 11.64 kilonewtons. The distance from F to G in the x direction is 3 meters. So how far to the right do you go from F to G? 3 meters. Divided by the distance from F to G in the y direction. Note this carefully. From F to G is not 6 meters, it's down 6 meters, or negative 6 meters. So this value here is just 1/2. So if I take 11.64 kilonewtons, multiply by these two, note that the units cancel out. 3 over 6 is 1/2. Gx is negative 5.82 kilonewtons. Now I can take this value and bring it back over here to my forces in the x. So 0 equals Ax, which we don't know, plus Gx, which we just determined, plus Px, which is 9.66 kilonewtons. Combining those terms, zero equals Ax plus 3.84 kilonewtons, and putting 3.84 kilonewtons on the other side of the equation, Ax is 3.84 kilonewtons, and it is negative. Now that we've determined the components of each of the forces, Px, Py, to start off with, then we use sum of the moments about point A to get Gy, sum of the moments about point G to get Ay. We use the slope relationship at G, because Fg is a strut, to determine that Gx is negative 5.82 kilonewtons. And then we use summing the forces in the x direction to determine Ax. Now that that's all done, although we have all the components of all the unknowns, we need to find the resultants of each of the forces. P is already taken care of. It was given as 10 kilonewtons at negative 15 degrees. We need to do the same for Ax, Ay, to combine them to find the resultant at A, and the resultant at G using Gx and Gy. Give an example of A. Let's separate this out. And to find the resultant of a force when you have its components, so in this case A, simply use the Pythagorean theorem. The components are at right angles to each other, so we have a right triangle. So this is Ax squared plus Ay squared. Now this will give us simply the magnitude of the force at A, not the direction. If I draw the force, we have Ax of negative 3.84 kilonewtons. So there's AX, and AY is negative 9.05 kilonewtons. We have a resultant here, which is A. Here's our right triangle. In between, we will have an angle theta A. Now we will always be looking to find the angles with respect to the positive x-axis. We do this so that we have a consistent reference axis for all forces that we are considering. First, we will calculate the resultant magnitude of A. A equals square root of negative 3.84 kilonewtons quantity squared plus negative 9.05 kilonewtons quantity squared. Taking each individually, the first term is 14.75 square kilonewtons plus 135.5 square kilonewtons. Add them up. We have square root of 150.25 square kilonewtons and square root of 150.25, and we end up with 12.3 kilonewtons. Square root of a square kilonewton is simply a kilonewton. We will do the same with G. G will be the square root of gx squared plus gy squared. We'll just put the values here. Negative 5.82 kilonewtons squared plus 11.64 kilonewtons quantity squared, and G ends up with a magnitude of 13.0 kilonewtons. Now the magnitudes are important, but they're not sufficient. We need to also calculate the angles. I'll write our formula for the angle here. Now most calculators actually do not consider what quadrant the component forces are in. They do not notice the difference between a negative force in the x direction versus a negative force in the y direction. So we have to put that as part of our formula so that we don't get mixed up on our calculators. So the angle will be the inverse tangent of Fy over Fx. But if we have a negative force in the x direction, that means the force will be in either the second or third quadrant. And a calculator, most calculators, will only put the inverse tangent of a negative number in either the first or fourth quadrant. It will assume that any negative is a negative in the y direction, hence giving a false value. So we need to add something to it to remember our calculator's limitations. We're going to add 0 degrees if the force in the x direction is greater than 0, simply if it's positive. And we need to add 180 degrees if fx is less than 0. So our angle of force A equal to the inverse tangent of AY over AX plus 0 degrees if the x component is greater than 0, or 180 degrees if the x component is negative. Filling the values in. We have the inverse tangent of negative 9.05 kilonewtons over negative 3.84 kilonewtons. In this case, our calculator would cancel out the minus signs, leaving us with a first quadrant angle. But that's not what we have. Our diagram over here clearly indicates that we will have a third quadrant angle. Calculating this out, the angle at A is 67.0 degrees plus 180 degrees, yielding 247 degrees. Our angle for the reaction at G is similarly calculated. Take the inverse tangent of 11.64 kilonewtons over negative 5.82 kilonewtons, and because our x component is negative, we add 180 degrees again. Theta G is negative 63.4 degrees plus 180 degrees. So the angle of the reaction of G is 116.6 degrees. In summary, we use a variety of techniques to start with finding the components of the forces that were applied in the first place, then using the moments about A to find our reaction in the y direction at G. Then we found our vertical reaction at A, summing the moments about point G. The advantage of doing that around these points is that many zero terms were developed So all we had left were these as unknowns. Then we took the slope relationship of a strut and used that to determine the horizontal force at G. This would also work for a flexible support such as a cable. Then we use our forces in the x direction to find AX. To finish things off, we used our ability to calculate a resultant using the Pythagorean theorem, and then we calculated our angles for our reactions. This now gives us a complete picture of the reactions at G and A and the load at P.